Hi! We saw in a previous video that it is possible to take closer pictures of subject to see them larger on the sensor than it is possible with a regular lens when using some accessories like extension tube. What is an extension tube? This is just a spacer that we put between the lens and between the camera. These spacers are empty, there is no glass inside. Okay, so it is possible to increase the distance between the camera and the lens. This way we can get closer to the subject and get more magnification. Another way to do it is also to use photographic bellow. Bellow is exactly the same thing as an extension tube. It's a spacer that you put between the lens and that you put between the camera. So by using a bellow or extension tube, it is possible to get more magnification. Let's take this camera with this lens. Right now the lens is set at infinity. If I measure the distance between the sensor and the front of the lens, I am about 11 centimeters from the sensor. Now, if I focus that lens to its minimum focus, and by the way this is a macro lens, if I set this lens to its minimum focus and I measure the distance from the sensor to the front of the lens, I am at 14 centimeters from the sensor. That means that the lens have been moved forward 3 centimeters. If for some reason this magnification is not enough for what you want to photograph, if you need more magnification, then it is possible to use those extension tube or eventually the bellow. So the tube can be used one by one, or you can join them together to get even a longer close-up, a longer tube, and this way you can eventually get more magnification. So right now I attached 3 extension tube together. If I remove the lens from the camera, if I put those tubes on the camera, and then if I put the lens in front of the tube, I now have a longer extension that is, if I measure from the sensor to the front of the lens, 20 centimeters. That means by increasing the distance between the lens and the sensor, I will be able to get closer. Another way to do it is also to use a macro photography bellow. The function of this bellow is similar to the close-up, except that you can change the length of the bellow just by turning a knob and then get a specific length that may be useful for you. So why putting some spacer between the lens and the camera help us to get more magnification? I'm going to give you a demonstration. Don't worry, this is not mathematical. There is no complicated equation in this demonstration. It's only graphical. So just by looking at the graphics you will understand how light travels between the lens and the camera sensor. Before I explain to you how I draw a light path coming from a subject and going through the lens and finally creating the image on the sensor, I'd like to talk to you about the different kind of light we encounter. There is in fact 2 types of light that we see. We call it incident light and reflected light. Incident light is normally coming from a light source. Light source could be for example the sun, could be a light bulb or a light emitting diode, could be a candle. Reflected light comes normally from subjects that are not a source of light, but they do reflect incident light coming on them. For example, it could be a flower, it could be a mountain, a cloud, or simply an apple. So the incident light hitting the subject will normally be reflected, and among all those light rays that are reflected, some of those rays will come to the lens and will create an image on the sensor. Just want to mention that light is reflected in all directions, but we will consider mainly the light rays going through the lens. And there is two types of light rays going through the lens. We will see it later. There is light rays going parallel to the lens axis, and also the light rays that goes through the front focal point. Okay, to show you how the light rays path is made in front and behind of the lens, I'm going to use the theory of thin and simple lenses. I know that real camera lenses have a certain thickness, some thickness, and this is because those lenses are made of multiple lenses inside. We call the assembly is called a camera objective, and the internal element are called lenses. And I'm going to base the construction of the light path on the theory of the simple and thin lenses. Okay, what is a small and a thin lens? Here's an example. This is a lens. This is very thin, as you can see. This one is small. It could be larger. But to simplify the explanation, I will use a very thin lens, as thin as a line. To demonstrate that, I'm going to use a larger lens, still considered as a thin lens. It's a simple magnifier like the one you use to read text or whatever. And to show you how it works is what is the focal point is I'm just going to put the lens here. You might not be able to see it on the target, on the let's call it the sensor, because of the depth of field. But if I'm moving the lens away from the card, I will reach a point where the lens will be in sharp focus. Okay, now it's about in sharp focus. That sharp focus obtained with the lens on this side is about 14 centimeter or 140 millimeter. Now I will reverse the lens and do the same thing again. I'm just going to slide it down until I get a sharp focus. Okay, it's about sharp here. So if I read again the ruler, I will see that it is still at 140 millimeter or 14 centimeter. Where I want to go with that is simply to explain that a lens has two focal points, one in the front, one in the back, and those two focal points are the same. You will see later when we draw a light path for a lens how we use those two focal points. Okay, to illustrate the experience we just made before, I will put on the graphic what's happening inside, in front and behind of the lens. The thin lens is the blue line right here. Okay, that means it's a very thin lens, as thin as a line. And what happens is if you take a subject that is far away, light rays coming from that subject will always be parallel to the lens axis. So if we take on the red side, okay, light path from infinity are all coming parallel to the lens axis that is right here. Same thing below. And all those light paths, when they go through the lens, will converge, all of them, through a point at the back that is called the focal length of the lens, or the focal point. Same thing happens on the other side. All light path coming from far away at the infinity at the rear of the lens will also be parallel to the lens axis, and all those parallel paths will converge in front of the lens through the same point that is called the front focal point. So we have a rear focal point, we have a front focal point, and those two focal points are equal in distance in the lens. This is it. Okay, now let's draw some light path for a subject in front of the lens. That is, let's consider it as a far subject, and see what happens behind the lens when the image is traced from the light path. I choose a focal length of 50 millimeter. Could be anything else, but it's a focal length that most of us knows well, and I use a focal length of 50 millimeter, which means I got the rear focal point at 50 millimeters behind the lens, and I also have a front focal point in front of the lens that is also at 50 millimeter from the lens. I put my subject at 250 millimeter, okay, which is 200 millimeter in front of the front focal point. Let's draw some light path. Okay, the theory says that light rays coming from the front of the lens will have some parallel light path to the lens axis, and that ray will converge through the rear focal point, which is the black line here. It also says that the light coming from point A, again, will pass through the front focal point up to the lens, and then it will exit parallel to the optical axis. So the intersection of those two lines is point A. Let's do it for point B. Parallel ray coming from the front, so parallel to the lens axis ray coming from the front will hit the lens and then will converge through the rear focal point, which is right here, and light rays coming to the lens and passing through the front focal point will hit the lens and will exit parallel to the lens axis. The intersection of those two rays is point B. So what I want you to realize here is when the subject is kind of far in front of the lens, its image is kind of small behind of the lens, smaller than the original subject. So, and also there is another thing that you should see is that the image is reversed on your sensor. So large subject in front and the subject away from the lens will reproduce a smaller at the back. If I take the size of that subject here in the front is 1, 2, 3, 4, 5, 6, 7, 8 square high, and I take the same thing at the back, 1 and 2 square highs, that means that the magnification is 2 divided by 8, which is 1/4. So magnification is 1/4 or 0.25x. We can also calculate the magnification another way instead of using the height of the subject and the height of his image. The image at the back is at 62.5 millimeter. I have 1, 2, 3, 4 square for 50, and I have a fifth square for the focusing plane, and that plane is at 62 millimeter. So 62 millimeter minus the focal length 50 gives me 1/4 or 1/4, and this is another way to calculate the magnification. Okay, now let's make a second example of what we just did. It will be the same subject, 8 square high, but instead of being at 250 millimeter in front of the lens, it will be 150 millimeter. As we may expect, the subject may have to be a little bit further away from the lens than the first example I gave you just before. To prove it, just let's make some light path for that example. As I did before, in front of the lens, parallel rays will hit the lens and focus through the rear focal point. For A again, I will have a light ray that goes through the front focal point, and once it hits the lens, it will exit parallel to the optical axis. The intersection of the two lines gives me the point A on the image side. Now let's do it for the point B. Point B, parallel rays to the lens axis, hit the lens, and converge through the rear focal point. Same thing for the light rays that goes through the front focal point. It hit the lens and then exit in a parallel way, in parallel directions to the focal axis. Okay, now we have point A, which is the image of the subject A. We have point B, which is the image of the subject B. And if we compare the image size to the subject size, we will realize that we have 8 square high here, and we have 4 square high on the image side, which means that the magnification will be 4 on 8, which is 1/2 or 1 to 2 or 0.5x. As I showed before, now the focusing point is further from the lens than the previous example. Instead of being at 5 square behind of the lens, it's now at 6 square, 1, 2, 3, 4, 5, 6 square away from the lens, and that is a distance of 75 millimeter instead of 62.5 like the previous example. We also can calculate the magnification by using those information. 75 minus 50, which is the focal distance. 75 minus 50 gives me 25. 25 divided by the focal length 50, I get 1/2, which is also another way to calculate the magnification. So, to conclude on this drawing, if you move the subject closer to the lens in front, its image will be further away from the lens on the back of the lens. Okay, let's make a third example. This one is very special because we are studying the case where the subject is exactly the same size than its image on the sensor, which means the subject is life size, or what we call also 1:1 or 1x magnification. To do so, I will put my subject at 100 millimeter instead of 150 or 250, and 100 millimeter is exactly twice the focal length. You will realize then the subject is also twice the focal length at the back. But to prove it, just let's make the focal path let's trace the light path of the rays. If we take the point A, we draw a parallel line to the axis up to the lens, and then we converge through the rear focal point. For point A again, we go through the front focal point, hit the lens, and exit parallel to the optical axis. Intersection give me the point A. Let's do it for B. Parallel to the axis, then converge through the rear focal point, converge through the front focal point, and exit parallel to the lens axis. That gives me the point B, where the two light rays intersect. So, like I mentioned before, this is a specific case where the subject is at twice the distance from the lens than is the focal length, and the image is also at twice the distance in the back than it is from the focal length. And if we add those distances all together, the image is exactly four times the focal length away from each other. Just remember, we still have a thin lens. It does not work exactly the same with a real objective, but what happens in front and what happens behind of the lens is basically the same. So magnification is 8 square I, 8 square I, so 1 on 1 or 1x or life size. Another way to calculate it is to take the image distance from the lens minus the focal length of the lens, which is 100 millimeter minus 50. That gives me 50 millimeter. This is the extension. And the extension divided by the focal length, which is 50 millimeter, 50 on 50 is 1 to 1 or 1x. One last thing I would like to add to this specific subject here is that we made it for a 50 millimeter lens. So I said if you had 50 millimeter lens extension on a 50 millimeter lens, you will get a life-size subject. If you have a different lens, if you have a 100 millimeter lens, then the extension at the back will have to be also 100 millimeter instead of 50 to get life-size subject. And okay, now let's make a last example. This one is special also because what I did here, I kept moving closer to the lens in front of it with my subject. So if at 100 millimeter we had life size, we can expect bringing the subject closer to the lens, we will have a subject larger. We will have the image of the subject larger than the subject itself. To prove it, let's make the light path. Point A, we go parallel to the axis, and then we converge through the rear focal point. Then we go through the front focal point, hit the lens and go parallel to the axis. We do the same for B, parallel to the axis, and we converge through the rear focal point, and then we go through the front focal point, and we go parallel to the rear axis. That gives us point A and point B. If we calculate the number of square between this one and this one, we can see that we have here 16 square high compared to 8 square high. So 16 divided by 2 give me a magnification of 2 to 1 or 2x. So as I mentioned earlier, the closer and the closer we get to the lens with the subject, the further and the further the image will be sharp, and the larger is also going to be the image the further away we get away. To conclude my graphic demonstration of the light path and the magnification we obtain at the back of the lens, let's conclude it this way. The same subject, always 8 square high, has been photographed at different distance, 250, 150, 100 millimeter away and 50 millimeter away. In every case we got an image that was increasing in size while we were decreasing the distance from the camera. So when you decrease the distance, the image on the sensor is getting larger and larger, and also the distance between the lens and the image, the sharp image, needs to be longer and longer. Okay, so to do so we will have to add some spacer like extension tube or bellows. So this way, you, by increasing the distance between the lens and the sensor, will give you different magnification for the same subject at the front. I hope this will clarify why increasing the distance between the lens and the sensor will decrease the distance between the subject and the lens, and by the same way it also increases the magnification. Don't worry, you won't need to bring a calculator with you when you do photography or macro photography. The explanation was just there to help you to understand how it works inside of the camera, why we use extender, spacer, and maybe eventually if you do a little bit more math with it, it may help you to understand why we use extension tube when needed, or why we use a bellow, or why we may use some other type of equipment that I will eventually talk to you. If you enjoyed this video, do not hesitate to click on the thumbs up button. This way I will produce more of this kind of macro photography video. If you want to make sure that you won't miss any of them, just click on the subscribe button on there below. This way you will know when I do more and more video like that. Finally, if you have any photographer friend that are interested into macro photography, just tell them about my channel. Until next video, enjoy macro photography.